Imagine a supercomputer that's just not faster, but radically more efficient, tackling climate change and discovering new drugs. The key to unlocking this power isn't just better software, it's something incredibly small. Welcome to the world of Taiwan Semiconductor Manufacturing Company, or so called TSMC's 2 nanometer chip technology. My name is Kaveen, and today we are breaking down its benefits and the immense technical hurdles for high performance computing. For decades, the mantra in computing has been Moore's law, cramming more transistors onto a single chip. We measure this by the process node, like 7 nanometer, 5 nanometer, and now 2 nanometer. To give you perspective, a 2 nanometer transistor is almost 10,000 times smaller than a human hair. This is just about making things smaller, it's about making them fundamentally better. For high performance computing, where we connect thousands of chips to solve massive problems, this jump to 2 nanometer is a potential game changer. So, what does 2 nanometer actually get us? Three big things. First one is raw performance. TSMC promises a 10 to 15% speed boost at the same power, or a 25 to 30 reduction in power consumption at the same speed. For a data center using megawatts of power, that efficiency is a huge win. Second one is increased transistor density. We are talking about fitting over 20 billion transistors into a space the size of your fingernail. This means we can pack more specialized cores, AI accelerators, and faster memory controllers right onto the CPU or GPU die itself, reducing communication delays. Third one is enabling advanced packaging. With these tiny powerful chiplets, we can use technologies like 3D stacking, literally building upwards to create incredibly dense and fast systems, perfect for the massive parallelism in high performance computing and AI supercomputing. Now, achieving this isn't easy. The challenges are monumental. The first hurdle is physics itself. At the atomic scale, we hit quantum effects like electron leakage, where electrons tunnel through barriers they shouldn't. To solve this, TSMC is moving to a new transistor architecture called Gate All Around FETs. Think about it like changing from a fin on a surfboard to a full wraparound grip for a better control. This is a massive manufacturing shift. The second hurdle is lithography. To etch these tiny patterns, TSMC uses extreme ultraviolet lithography or EUV. But for 2 nanometer, they need high NA EUV, a new, vastly more complex and astronomically expensive machine. We are talking hundreds of millions of dollars per machine, which leads the third hurdle, cost. The design and factory costs for 2 nanometer are stratospheric. This means only the biggest players like Samsung, Nvidia, and AMD can afford these chips, which would slow down how quickly this takes spread through the high performance computing community. Despite the hurdles, the push is on. The next generation of exascale supercomputers will likely be built on these 2 nanometer class chips, allowing for more realistic simulations of everything from global weather patterns to the fundamental laws of universe. In conclusions, TSMC's 2 nanometer node represents a classic dead trade-off, revolutionary potential versus extreme complexity. It will deliver the raw speed and efficiency that the future of HPC and AI demands. But mastering the atomic scale manufacturing required is one of the hardest engineering challenges humanity has ever undertaken. So, thank you for watching. If you want to dive deeper, you can check out the sources I used, linked in the description below. What do you think? Will be the benefit outweigh the cost? Let me know in the comments.